Hello, my name is Mitchell Lord, and this is my Lab 1 presentation. As an introduction, the purpose of this lab was to analyze the motion of an object moving with approximately constant velocity using Newton's second law. I conducted this experiment by rolling a standard basketball across the floor while recording it with a stationary camera. I then analyzed that video on Tracker to obtain position versus time data, and then I created a computational model in GlowScript based on Newton's second law and compared the predictions versus the observations. And here's a brief overview of my results. The white line is my observation, and the red line is the computational model. So as you can see, they do closely approximate one another. The physics principles used here are centered around Newton's second law, F equals ma. As we can see from this equation, that a net force of zero implies acceleration of zero, which is the definition of constant velocity. Other equations used, obviously Newton's second law, and both the velocity and the position update formulas are direct consequences of Newton's second law. For the setup, the basketball is the system. Everything else, like the earth, the air, and the floor, are the surroundings. I placed the coordinate system at the center of the basketball on the first frame of the video. I also used a 10-inch tape measure to calibrate tracker. The initial conditions were position at the origin. The initial velocity that I got from tracker was 0.6300 meters per second. The initial time was 0. Here's the actual video. Alrighty. So I then plugged that video into tracker, calibrated it with a tape measure, and set the origin. I then went through frame by frame, marking the center so tracker could model its motion. And then I took some of the values from tracker and input them into GlowScript. I made variables for mass, initial location, and velocity. And then I started a while loop and iteratively calculated and updated the position and velocity of the ball using Newton's second law with a net force of 0. And then I got both of the data from both of them and made this chart. So as we've already seen, the red straight line is the computational model, and the white slightly squiggly line is my observations. They do closely approximate one another. This does indicate that the velocity of the ball during its motion is approximately constant, and the net force on the ball is approximately 0. The small differences in the observation line are likely due to measurement uncertainty and experimental error. Possible sources of this error could be a tracking marker error. Me having to manually mark the center of the ball each frame could obviously cause some error. Could be a calibration error if I didn't precisely calibrate tracker right. Um, Also, a video resolution error limited by camera resolution and frame rate may reduce measurement precision. And the surroundings, like the floor, the earth, the air, could have all played an effect on making the velocity not strictly constant. So, what if the axes were flipped? Well, if the axes were flipped, all position and velocity values would change sign. The position versus time graph would have a negative slope. The magnitude of the velocity would not change, and the computational model would still agree as long as the initial velocity and coordinate system were updated accordingly in the code. What does it mean? Is it possible for you to say how many forces are being added together? No, not in this case. The approximately constant velocity of the ball indicates that the net force on the ball is approximately, but not exactly 0. However, it is not possible to determine how many individual forces are being added together to produce this 0 net force. For example, there's gravity, the normal force, small frictional and air resistance forces. However, this video alone does not allow us to determine exactly which forces are present or how many there are. In conclusion, we analyzed the motion of a basketball using tracker, made a computational model in GlowScript using Newton's second law, and we found that the model closely matched the experimental position versus time data. And these results support that the ball moved with approximately constant velocity and experienced approximately 0 net force. Thank you.